So lesson 2.2/2.3 is on examining the instantaneous rate of change. That we want to first look at what is meant by a tangent line. So if you look at the diagram here, you have a curve, this blue graph over here, and you have 2 points in the graph. And we saw from our previous lesson that this is a secant line. And if we find the rise over the run, or the change in y over the change in x, we have the average rate of change of the secant line. What if we didn't want to find the slope of a secant line? We want to find the slope of tangent to the curve at a point. So a tangent line would look like would pass the curve at only one point. So this would be a tangent line. As you can see over here, it is passing through this point at just one point. Let's call this point P. What would the slope of this line be? That would give us the instantaneous rate of change. The tangent line, which is touching the curve at only one point, would give us the instantaneous rate of change. The exact rate of change of a function y equals f of x at a specific value of the independent variable x equals a would be the instantaneous rate of change at that value a. So what we're going to do to find the exact value of the rate of change or instantaneous rate of change is going to be difficult to find the exact value unless we're using calculus. So what we're going to be doing is the methods we're going to be using to find IROC is going to be an estimate. And we're going to use the average rate of change and then use that to kind of arrive at an estimate of the instantaneous rate of change at one point. So let's look at how we're going to work around that. So let's say we have a question. We're going to do this investigation question. How can you use the slopes of secant lines to estimate the instantaneous rate of change? So you see here, you have a question. A golf ball is lying on the grass and it's hit so that its initial velocity, vertical velocity, is 25 meters per second. The height h in meters of the ball after 3t seconds can be modeled by the function h at t equals negative 4.9 t squared plus 25t. What is the instantaneous rate of change at 1 second? Okay, so what we're going to do is we need to find the instantaneous rate of change at 1 second. So we have this this function. What I'm going to do here is just draw a rough sketch to explain what's going on. So let's say this is our graph, the path of this golf ball. And let's say this is our h at t, this is our t, and let's say this is 1 second, and we want to find the slope at 1 second. So we're trying to find the slope of the tangent line here. What would be the IROC at 1 second? That's what we're trying to determine. What we're going to do is we're going to take values that are very close to 1. So let's say we take a value that is, and on all the values we're going to take are to the right of 1. So we could take a value, let's say this is another point to the right of 1, this is 2 seconds. And then we're going to find the slope of the secant line that connects these 2 points. Then we're going to get a little further closer to 1 on the right side. So we're going to say go to 1.5 and find, I'm going to use another color here, find the slope of that secant line, right? And then we're going to get even closer to 1, let's say 1.1, and maybe it'll be somewhere here, and then find the slope of that secant line, and then get even closer, let's say between a line between 1 and 1.01, which would be very close to 1, and find the slope of that line. And then get even more closer to a line that connects 1 and 1.001, which is extremely close to 1. And as we get those slopes and we kind of narrow the distance from 1 to the next point, we're actually going to get closer and closer to this line, which is the tangent line to the curve at 1 second. So that's the method we're going to do. It's going to help us arrive at an answer, which will be an estimate because it's not an exact answer. Okay, so we're going to use the same idea. It's going to find the change in height over the time, so delta h over delta t, and see what our values of AROC are getting closer and closer to, and that will help us get an estimate of the instantaneous rate of change. So the change in height between the intervals of t greater than or equal to 1 and less than or equal to 2 will be another change in h, which is h2 minus h1, right? And that would be using this equation that we have for height. We are going to plug in negative 4.9 times 2 squared plus 25t minus h at 1, which is negative 4.9 times 1 squared plus 25 times 1. So when we do that, we're going to get the answer as 10.3. I've already done it earlier, so I have the answer. And the change in time will be, 2 minus 1, which is going to be 1 second. So our AROC between these two intervals is delta H over delta T, which is going to be 10.3 divided by 1, which is 10.3. And we have units here of meters for height and seconds for time. So it's 10.3 meters per second. Now we're going to take a value even closer to 1, so between 1 and 1.5, and find the AROC between these two values. So it would be H at 1.5 minus H at 1, which works out to 6.375. And the change in time is 1.5 minus 1, which is 0.5. And delta H over delta T, if we calculate, works out 12.75 meters per second. So you can see that this value is kind of very different from that value. So let's get closer to 1. Let's find the slope or the average rate of change between 1 and 1.1. We're getting even closer to 1 there. So it's delta H is H at 1.1 minus H at 1, which works out to 1.471. And change in time is going to be 1.1 minus 1, which is 0.1, and we get 14.71 meters per second. Again, we are kind of very different. This was 10.3, then it became 12.75, and now it's 14.75. Now we're getting even closer and finding the AROC between 1 second and 1.01 second. The change in height is H at 1.01 minus H at 1, which works out to 0. Just going to take that off. 0.15151, and the change in time is 0.01, and delta H over delta T is 15.151. And now we're getting even further closer to 1, so we're going to find the AROC between 1 and 1.001 second. So delta H is H at 1.001 minus H at 1, which works out to 0.015191. This is 0.001. The AROC is 15.1951. So now you can see that the values, the last two values there, if you approximate them to 1 decimal place, they work out to approximately 15.2 meters per second. So you can see that now as you get closer and closer to 1, the AROC value is approaching 15.2. So our estimate of the instantaneous rate of change is about 15.2 meters per second. So therefore, we will conclude that the IROC, which is a short form of instantaneous rate of change, at t equals 1 second is 15.2 meters per second. Okay, so that's how we find out the instantaneous rate of change at a given value of time for this question. So we cannot find the exact value of IROC at a point, so therefore we're going to use the method I just showed you here, where we're going to find the slopes of, or the rates of change, or the average rate of change of secant lines that are very close to the value that we want. And then we shorten the distance so that we can get even more closer and closer to the actual value or of the instantaneous rate of change. So the same idea, that we cannot find the slope of the tangent because we only know one point on the tangent line. And as the point, um, let's say this is our point P and this is our point Q, we are going to move this point Q closer and closer to P. And so the slope of this of the secant line PQ approaches the slope of the tangent line to the point P. So that's the aim that we are going to, or the strategy we're going to use to find IROC. The best estimate occurs when the interval used to calculate the rate of change is as small as possible. So we want to make that interval really small. So if you look at our previous example, the interval when we got closer to IROC was when it was very small, like the 0.001 was on the change in time. So we want to shorten that interval. We want to shorten that distance between 1 and the next number beside it. So if we want to know the instantaneous rate of change of f of x at x equals a, consider the intervals between x equals a and x equals a plus or minus h, where h is a really small number, and then we can use this formula to find the instantaneous rate of change. This formula is called the difference quotient. So to understand that, I'm just going to draw, let's say I have a curve like this, and I want to find the value or the IROC at this point P. I really essentially want to find the slope of the tangent to the curve at P, which will be something like this. I want to find the slope of this line, right? The slope of this line will give me the instantaneous rate of change at point P. So let's say at point P, this point is A here. And then I take a point very close to P, and let's say that the distance between A and the next point here is just a very small number h. So that distance here would be A plus h. Okay? And the corresponding y values for those A and H plus A plus H values are f of A for A and f of A plus H for A plus H, right? So that's my corresponding y values to these x values. So my delta y would be f of A plus H minus f of A, and my delta x, or the run, would be A plus H minus A. And when you do A plus H minus A, as you can see here, the A minus A will add up to give you 0. You're left with just H in the denominator. So this is the formula. It's also called the difference quotient that we can use to calculate IROC. So mathematically, we're going to select points closer and closer to the point P. We're going to calculate the slope of each secant, and the slope of the secant will approach a value which is the slope of the tangent. Let's try an example. Estimate the instantaneous rate of change of f of x at f of x equals x squared at the point x equals 2. There are several methods that we can use to find, intervals. So we can use intervals that are just before and just after this point, x equals 2. We can choose an interval where we go from 2 to an interval just after it, or we can choose an interval before 2, so 2 and an interval before it. So there's several methods. So we can choose any one of the methods that we want. I'm going to use the squeezing method, which is the squeezing technique, which is we're going to choose points on both sides of x equals 2. So there's a point just before 2 and a point just after 2, but very close to it. So first I'm going to choose values that are a bit further away from 2 and find the IROC values. And then I'm going to narrow their distances and get closer and closer to 2 so that I get closer and closer to the IROC at x equals 2. So first I'm going to start with a value, let's say between 1 and 3, and 2 is halfway between 1 and 3. So every interval I take, it should be equidistant from 2. So if I go all the way to the left as I go at 1, then I have to go all the way right to 3. So that 2 is, in the middle of that. So I'm using the midpoint of intervals technique here, which is also called the squeezing technique. So this is my interval, and my IROC at that interval is change in y over change in x. So it is f of 3 minus f at 1 divided by 3 minus 1, which is 2. And I have the function is f of x equals x squared, so f of 3 would be 3 squared, which is 9, minus f of 1, which would be 1 squared, which is 1, divided by 2, which is 8 divided by 2, which is 4. Then let's get closer to 2. So let's get an interval 1.5 less than x less than or equal to 2.5. So you can see that I'm now, but from 1 to 3, I've now got even closer, 1.5 to 2.5. So it's 2 is the middle of those two intervals. The AROC at that is f at 2.5 minus f at 1.5 divided by 2.5 minus 1.5, and I find that my AROC value is 4 there. So you see how it's very similar. Let me get even closer to, let me get to just 0.1 before 2 and 0.1 after 2. So x is between 1.9 and 2.1. Then the AROC would work out to f at 2.1 minus f at 1.9 divided by 2.1 minus 1.9, which works out to, again, 4. So you can see that my AROC values are consistently 4. So therefore, I can conclude that the instantaneous rate of change at x equals 2 is 4, because I approached it from both sides and it kept giving me 4 in each case. Now, there's no units for AROC because they haven't given me units in the question, but if they did give me units, I would be using that in my answer. So let's try an example. A soccer ball is kicked into the air such that its height h in meters after time t seconds can be modeled by the function h at t equals negative 4.9 t squared plus 15t plus 1. A, determine the AROC over the interval t greater than or equal to 1, less than or equal to 3. And part B says estimate the instantaneous rate of change when t equals 1. And C, for this situation, what does the AROC represent when t equals 1? So let's do the first one. The AROC between these two intervals is h at 3 minus h at 1 divided by 3 minus 1. And then using this equation for height, it's going to be negative of 4.9 times 3 squared plus 15 times 3 plus 1 minus h at 1, which is going to be negative 4.9 times 1 squared plus 15 times 1 plus 1 divided by 2. And you plug that in your calculator and you get negative 4.6 meters per second. So there's units here because height is in meters and time is in seconds. Okay. Now they want me to also find out the AROC at the value t equals 1. So we're going to take values that are very close to 1. So let's say that I'm going to use the quotient method, or this one here, the difference quotient to find AROC, f of a plus h. So I'm going to take an h value which is very small and just to the right of a, and then use this difference quotient. Okay, so that's the method I'm going to use here. So I'm going to use difference quotient, and therefore my AROC will be f of a plus h minus f of a divided by h. In my case, my a value is t, so it'll be f of t equals 1. So it'll be 1 plus h minus f of 1 at divided by h. So we have to decide how small our h is going to be. Let's say let our h be very small. Take a small number. Let's say 0.1. Start with 0.1. Then the AROC would be f at 1.1 minus f at 1 divided by 0.1, which when we plug it into this formula or this equation we have for the height that's given to us in the question, it actually works out to 11.571 minus 11.1 divided by 0.1. Now, that's a lot of work there that I've condensed. I've already done it before. So what I would ask you to do is actually, when you're doing the study, pause the video here and write out the entire equation, put the value of 1.1 and then put the value of 1 and actually compute it. So you're practicing how to do it and you know how to do it in your calculator. This works out to 4.71 meters per second. Let's get even closer to 1 by taking an interval that's even smaller than 0.1. Let's make it h at 0.01. What would the IROC be? Just to compare and see if we are very close to it. So this would be f at 1.01 minus f at 1 divided by 0.01. And that would give us 11.15151 minus 11.1 divided by 0.01. And that gives us approximately 5.2 meters per second. So I'm going to take this as my answer because it's a very small value of h. And so I'm going to conclude that that is the value of the IROC at t equals 1. Part C is asking me, what does it mean to have this answer? What is the meaning of 5.2 meters per second at time equals 1? Well, it actually means the speed of the ball, right? So if you have a soccer ball and you would draw a rough sketch of the scenario, let's say the y-intercept in this question is 1. So this is 1. This is the height as a function of time. It's time over here. It reaches a maximum height and comes back down, right? That's the path of the ball. And let's say they're asking you what is the instantaneous rate of change at x equals 1. So let's say this is our 0.1 second. They want you to find, let's say you have, you want to find the slope of the tangent of the curve at this point. That's what you're trying to find. So at 1 second, what is the speed of the soccer ball? Right? That is what we are getting at when we did the IROC. So we're going to say that the IROC represents the speed of the soccer ball at 1 second, which was found to be 5.2 meters per second. Okay. Now we're going to practice